But they are still there. Never mind. I think this is a recorded session. I think they can find their way here eventually. All right, let's begin now. Let me share my screen. All right, let's see. Okay, everyone. Let's see. Let's look at the first thing. Let's look at our question first. Q3 is another alternative to Thevenin. It's called the Norton theorem. So Norton theorem is slightly different. I think it's quite opposite. Instead of just focus on the voltage and resistance, Norton will look at the current and resistance. And if you try to see the difference here, Norton would be start with the current source instead of the voltage source, and for the Norton resistance is in parallel. You see, it's not in series; it's in parallel. So somehow the way how they operate is slightly different. So it depends on which one is more suitable. Usually, I would prefer Thevenin. You see, I seldom use Norton. So Norton does appear as another alternative to Thevenin, where we look at the current and resistance only. So we have to presume that we have one fixed circuit. Let's give a brief preview about this circuit. So we have presume that we have a fixed circuit here, which to be attached to another external load. Okay, we always call this one is a variable, RL or something, variable load. And this time our circuit is slightly complicated. You can see instead of just a couple of resistors, now we have more than one. So it looks like this circuit here, if you focus on the right hand side here, you can see we have ABCD terminals. A bit confusing. Basically, what it means is the terminal B and C are attached to the external load. Okay, it's not part of the circuit, but eventually you are combined become a whole circuit. But from the Norton point of view, we only look at the one on the left hand side. When we try to find the equivalent Norton circuit, we will not look at the RL. We only assume this one is the external, which will be replaced by the user. Okay, so we're going to leave terminal A and terminal D open to be attached for the user to attach their load to the output side. So this appear to be the output side. So we have input side powered by 15 volt, and then we have this funny resistor network. You see at the glance, I think you may notice that these three resistors, they form a star connection. You can see that, right? They form a star connection. What I mean star connection is by looking this way. It's an upside down star connection. So this is the star connection will look like this one, right? It look like a star, not exactly a star, but this one is actually some call it star connection, but some call it Y connection. Okay, it's an inverted Y. So you can, if you look at this one, okay, let me give brief you about this circuit, the background information. If you look at this one, and this one, it look at like a Y connection. Actually, we can convert this one to the delta connection using the formula you learn in the section 1. You learn in the tutorial 1. You can convert this one. Let's say you call this one R1, R2, and R3. Okay, we can convert this one into RA, RB, and RC. Okay, RC. When you do that, you actually can simplify this circuit further so that it will make it easier for you to to calculate, to manually calculate the value, you know, for the Norton equivalent resistance. Okay. Otherwise, it's very difficult. I don't see any other way after any other than using the conversion like this. If you try to analyze it without using the any computer, just use your head. I don't think there's any other way can make it easier than this. See, after you convert it, okay, it will look like this. It will look like something much easier. I think probably we're going to talk about this later on. But for now, we just go ahead and construct this circuit, okay? And later on, when we being asked to calculate the theoretical value here, I mean this box, then when the time comes, it's a time for us to convert this circuit to another form so that it make it easier to compute our theoretical value for the Norton resistance. Okay, so let's go ahead and start from the original circuit. So I would just copy this one, you know, like before. Just copy this the title and continue from the previous one. So this previous one is until the Lab 2, right? So it's just continue from here. Continue from here, and I'm going to what? Insert page break. So here. Okay, then I insert this one in. Okay. Starting with the introduction section. I think this one you have to do yourself. I'm going to use most of my time on the lab session, not on this report writing. So let's see. Let's come back here again. But I'm going to show you some example. Caroline, then the Norton. Okay, let's just this sentence looks like more relevant. Let's copy this sentence as a part of the introduction. Remember to. Hey, wait a minute. This is 15 marks, huh? I thought every question is 20 marks. Let me double confirm. They mean if this one 15 marks, that means other question must be 25 marks. Yeah, there must be some question 25 marks. Otherwise, it doesn't make sense. This is another 20. Wait a minute. This question 5. Question 5 20. Question 4 20. Question 3 15. Wait. How can I get 15 every time? Stranger. Every time I copy, it becomes 15. What's wrong actually? What's wrong with this copy and paste? Every time I copy, it becomes 15. It's kind of confusing. This can be some viruses doing the trick here. Just to modify when we try to copy something, try to modify it. Otherwise, that doesn't explain this this kind of behavior. Never mind. Let's continue. Okay, let's continue. Let's continue with this one. We need this thing to explain the Norton theorem. Okay, this is a must. This figure is a must. Let's put this in. Put this into our report. Figure 3.2. So I will not continue to to work on this introduction. So you have to do your own. Okay, I just leave a message here. Alright, I'll continue with the procedure. Just highlight it. Okay, highlight it, bold it. construct the circuit in figure 3.3. Come on, let's see. Okay, construct circuit. Oh, this is not the font I want. Let's put the font I want. Okay, I think I need that figure 3.3 here. Before I forget, let's put this in also. Figure 3.3. We are kind of like recompile the worksheet into our reports. So we have a 3 dot here. I think it's okay. It doesn't bother us right so much. Okay, the space here is a bit outward actually. Probably you need to reduce it a bit. Otherwise, the space there is a bit outward, right? The space there. But once you insert something, probably you'll push out the thing all the way down. It's okay. We just leave it like this. Okay, it's okay. Now let's construct this circuit. Okay, let's save first. Save. And then we come here. We save our already been saved question 2. Now I just need to save as. Wait a minute. What do I do? Yeah, I think go ahead and save with question 3. Save in question 2 first, and then save as question 3. So by doing this way, we create another file for question 3. Okay, make sure it's Q3. Now we need to reconstruct everything again. Let's delete, use a scissor to cut all the things. See, with a scissor, we remove all the component here. We just left the power supply. Will do. The operating point, I think we still need operating point. Okay, just leave it there. No, never mind. Just go ahead and change it to 15 volt. All right, then we need the resistor network. 1, 2, 3, 4. What do we need to keep the 180 ohm? Let me see. Let me see. Do we need to keep that or not? Remove. See, immediately we need to remove RL. Remove RL from the network. Then we determine the current. Okay. Looks like we don't need the RL. We just construct 1, 2, 3, 4. Okay, so we 3 horizontal, 1 vertical. Okay. Hey, wait. One more here. 1, 2, 3, 4, 5. Let's start from here. Let's start do it one at a time. Okay, don't worry. Let's do it one at a time. Register. This is the first one. Make sure it's R1. But right now we do not have R1, R2, R3 anymore. You see, we do not have R1, R2, R3 to refer to. So it's okay to put anything anywhere you like. They just name them by the value, not name them by the special name there for the R. So there's for the top one, I need to rotate it. I put it here. Okay, and then another one here, another one here, another one here. So make sure to line them up properly. And the one in the center, I think, yeah, in the center. I need to rotate it. Place in the center. Okay. Then the ground, only one ground. It's okay. I can use this ground. So I can go ahead and join the wire. Join all the components. Okay, it's getting easier now. Use only one ground is okay. Ground we place at the left hand side. It doesn't matter if you place it in the center or the left hand side, on the circuit perspective is still the same. So we put it here. Now we have to find the current. Wait. We have to find the current, right? Let me see. Where determine the current value? So we need to measure the voltage point between A and D. So here's A, here's D. Let me extend this wire out a bit. Okay, let me, I don't know they allow me to do this or not. Extend the wire like this. Okay, let me put the text A and D so that people understand where is A, where is D. So A is referring to this node here. D is here. D is here. Okay. Now this not we can't do simulation yet. We need to fill in the value, collect value. 100 here. 100. $3.6K. What is 180? 1.8K. Okay, here to do the same. And follow exactly the same 820 and 100. Right. Forget about the 180 here, which represent the external load. Okay, forget about this. So now we have done this first part. I think we have to save it. We have to save it under the step one. Under the step one, construct the circuit below. Actually, you should say ignore the RL. Then never mind. Let's copy this circuit. Let's copy this circuit and paste it under the result. Okay, let's create one called results. And we type something like the simulation circuit. Simulation circuit for step number 1. Too big, resize it. I don't think we need to put a figure or anything, right? But it's good to do that actually. Let's find out the last one, the last figure number. Looks like it's very short. We only have 3.3 here. Let's continue with 3.4. 3.4. Simulation circuit for step 1 is shown in figure 3.4. Change it to the bow and 14 point. Okay, so let's consider step 1 done. Now proceed to step 2. Let's copy step 2. For step 2, remove resistor, and resistor is selected as the resistor. Resistor R is selected as the resistor where it's proposed. Proposed to determine the current value. Never mind, just copy it. Okay. I think we should proceed to step 3 now because the step 2 doesn't mean anything. We just say remove the RL. Okay, step 3 tells the exact instruction we need to follow. Let's start with, from step 3. Okay, run the simulation by performing the operating point. Same thing, same analysis. Measure the voltage between terminal A and D. I'm sure we can measure the voltage here because we have the ground. We have the ground at this node. And then we must be able to measure the voltage here, I suppose. Okay, let's do that. Let's run it. Yeah, operating point, double check operating point analysis. Okay, so we can just scroll this down. Actually, we can copy this simulation result actually. Okay, I think just go ahead and copy this simulation result. Otherwise, you may be end up with the paper question whether this is your, do you actually run a simulation or not, or you just copy the result from somewhere else. So we copy the whole window here. We copy the whole window here. Okay, we'll copy the whole window, and then we put it in under the figure 3.4. We'll put it under 3.4 here. We just say that the simulation result or step 4, is it step 4 or step 3? Step 4, step 3. Is shown in 3.5. Okay, it's down here, figure 3.5. All right, done. Now we need to worry about how to print out the V out at the terminal A and D. I think you know how to do it, right? So first, it's already running, the simulation is already running. So what we need to do is point the mouse at this node and then click. So it shows 4.88. Is it correct or not? Let me double check. Let me double check. 4.88, is it correct number? Remember this is a Norton theorem where we are not looking at Norton. There's no Norton voltage. We have Norton current only. So it is 4.88 valid or not? Wait a minute. Looks like this is not what we want. Looks like this is not the what we want. What do I mean? Because you had to, you see, this doesn't make sense. You see, by looking at the following steps, you said this is the Norton current, but what we are measuring here is a voltage. How can we measure a voltage and we're getting a current? So it doesn't make sense, right? So it looks like this is some typo or some mistake they made in the lab procedure. Okay, never mind. We need to change this one. We need to change this one and rectify this problem. Okay, let me guide you how to do this. That's why you need to attend the lab like this so they know what to do. So we need to change this one to measure the voltage. I think we're still measuring the voltage. I think we're still measuring the voltage. Okay, but what we do is we need to put in an additional component. Okay, Norton current. There's some step missing here actually. There's some step missing. This statement you can say is correct. This statement is correct, but there's something missing in between. That is, we need to insert a dummy resistor. Say from here, we insert a statement like here. We put the statement right before this statement. Insert we call the dummy 1 ohm between A and D. Okay, we need to insert another statement here. Okay, just go ahead and do this right now. Just go ahead and do this. Go to the position number 3. Okay, insert one more statement here. One ohm between terminal A and D. Then measure All right, so this is the new statement. You need to insert it. You need to insert between the original. Okay, let me highlight this one by put underline. Oh, I hate this thing here. See, I need to solve this problem. Never mind. So let's go ahead and insert the. When we do that, our previous circuit no longer appropriate here without the resistor, right? No longer appropriate. Later we need to recreate this one with the new one. Okay, just go ahead and put in one dummy resistor. Okay, put in one dummy resistor here. Yeah, like this. Because we try to, what we want is the Norton current, remember? We don't want the resistance, we don't want the voltage. What we're looking for is a Norton current. All right, change this one to 1 ohm. Why I choose 1 ohm is because it's easy to divide by 1. Anything divided by 1 is 1 divided by the number, instead of 2 divided by, I think 1 always a better choice, right? Let me move this one away here. Let me see, I can use the F7 and move this one away. Okay, now it needs another simulation. See, like this question here. Let's run that one more time. Run one more time. And looks like here is the question mark. Okay, let's remove this one. Let's change it to this is the R6. Let's find the current flow through the R6 because we are looking for the current, right? Let's find the current flow to the R6. Or we can also find the voltage here also. The voltage at the point A. Let me try this method first. Let me try to remove this one and then let me try click on here again. Run and click on here on the terminal A. So I have a different value, of course, now. Let's press F7 to move it to a better place. So this is the voltage, or this is what happened when the out of position, you see, you have this issue. Let's try one more time. Let's move to some other place. Oh, it doesn't help. Okay, let's do it again. Probably we shouldn't move it. Let's try again. Let's click on this one. Let's say we can move it above here. No, we still cannot do this. You see, I don't know why, but this is not our fault. You see, this is the limitation of the software. So it looks like what we can move is the A. Let's move the A away. Okay, then we click here. So this is the voltage here. So it looks like we can take the voltage and then we can divide by 1. I equal to V over R. Okay, let's come back to our procedure here. Looks like I need to modify something. So it says that insert the dummy resistor between A and D. Make sure the voltage between A and D. So we did that. And then proceed to number 4. Number 4. Okay, number 4. Copy this statement. Can you do that? Copy this statement, but we have to insert something in front here. Take Norton current to compute Norton current. Okay, divide the voltage by the resistor. Okay, the resistance. Okay, so any calculation, we better do it in the result section. So let's remember is the step 4. Where is it? Oh, here remember to replace it later on. Okay, calculation for step number 4 is IN Norton current is equal to I equal to V over R is what we measure is 7.870 millivolt divided by 1. Okay, let's see whether this is correct or not. I hope there's no surprise. Good, let me touch my calculator. 7.870 milli divided by 1. We get 7.87 milliampere. 7.87 milliampere. Is it correct? Let me double check. Yeah, it's correct. 7.87. So this is our answer, or Norton answer. This is the correct answer actually. Just underline. Okay, we need to replace this circuit. It's no longer represent the step 4. This step 1, right? This step 1. So we need to insert the simulation circuit for step 4. Is it step 4 or step 3? Let's find out. Or step 3. Simulation circuit for step 3. Okay, just do it one by one. Simulation circuit. Okay, let's import this one. Import it here and resize it. All right, guys. I think you can just, because anything divided by 1, you get the same number, right? Everything divided by 1 is the same thing. Okay. This is how we get the Norton current by using the Ohm's law again, and use a dummy load 1 so that we can apply our Ohm's law. Because if we leave it open, you know, what we get is a voltage here. And since there's no current here, it's hard for us to calculate the current flow through the output. What we try to measure actually is the current flowing through the output terminal, which is terminal AD. You know, we want to find the current flow through the output. That will be our Norton current here. Norton current. Where is it? Where is Norton current? Here. Okay. Now let's proceed. Let's proceed to the step number 5. Okay, a bit confusing here. So we have up to step 10. Okay. Let's do it. Step number 5. Let's copy first. Don't worry about the detail yet. Step number 5. Step number 5, what we want to do is, I think, to look for Norton resistance, right? So because we already got the Norton current, so what we're looking for next is the must be the Norton resistance, because this is the two that we want: Norton resistance, Norton current, and then eventually we find the current flow through the external RL. Okay, so I think the next step should be this one. Let's see whether it's correct or not. Switch off the power supply by stopping the simulation. Replace the 15 volt with a short circuit. Okay, just follow that. Just follow step 5 here. Remove this one because we want to find resistance, right? So we need to remove all the power supply or the current source. Okay, if there's current source here, we need to remove it. So let's remove this power source, leaving all resistance only. But we cannot let it open. It's an incomplete circuit. It's open circuit, so we need to connect a wire. And then it looks like we need to remove this one also. I think we need to remove this one. Because just now the 1 ohm is, we use the 1 ohm here to simulate the Ohm's law. So I don't think we don't need this 1 ohm anymore. We need to find the all the resistance here. Looking from here, just like Norton, just like Thevenin, we want to see the total resistance here. Looking into this terminal AD, what is the total resistance here? Okay, I think this is what we need to do. But of course, you cannot just run it and then show the resistance here, right? There's no such feature. You can see even though you click here, you run this thing, you get all the 0, and then you try to modify this one. You can see there's no resistance here. What you can get is only is either voltage or current. You cannot find resistance here. You cannot ask the software to print out the total resistance here. Okay, it doesn't work that way. So we have to use another method here to get our result, our total resistance for this circuit. So what is the method? Let's follow the procedure. Now we need to connect 1 volt. You see, we need to use external 1 volt again as a dummy. Use DC supply between A and D, and measure the current flow through it, and then we use the Ohm's law to convert the resistance. So I think the trick is the same. We're using the same trick. That means we're using the 1 ohm or 1 volt or whatever dummy. We call the dummy component, and then we so that we can apply our Ohm's law to find the resistance. So this will be step number 6. Okay, let's get the instruction in first. Let's get the instruction here. Then we Then we start for worry about the circuit. Okay, so he said put the 1 volt between A and D, and then measure the resistor. Okay, I think you roughly you know what to do, right? So just put 1 volt here. Still remember now is located here. Edit components, then voltage. Okay, so place it at this gap here. Then change this one to 1 volt. If you don't change to 1 volt, I don't think you will get any result. Change to 1 volt. So what we mean by resistance is a resistance is equal to voltage divided by current. Then come the drawing board now. As a beginner, I'm strongly encourage you to remember this their relationship proposed by the Ohm's law. Resistance is equal to V over I. So if we can measure the resistance between A and D, A to D, if we can measure the voltage between A and D terminal, and then if we can find the current flow through the wait, the voltage is already one volt here. It's already 1 volt. We force it to using 1 volt here as our power supply. And then what we need to measure is the current flow through the A and D. The current flow through A terminal A and D. Then we can determine the R, right? So it's this easy. Okay, so let's do that. Let's find the current flow through A and D. If you wonder whether the current can flow through the power supply or not, of course it can, right? Of course the current can flow through the power supply. So what we need to do is right click here, and we need to throw away the dollar sign. We need to see or here, this one is it, which one is the N1, N1, N2? We have 3 voltages here. We want to make sure this is the one we're looking for, V1. But there's no V1 here. Never mind, let's run the simulation. Probably you can see the V1 here. Yeah, now the thing appear already. You also appear the current also. The current flowing through the V1. But we can do that by click on the click on here. By convert it to IV1. Throw away the dollar sign. Click on the IV1. We just need one only. And then you'll show the current here. Okay, but this is not the final answer, as you know. 1.614. Let me see whether this is correct or not. 1 over 1.614 milli. So what is the resistance? Let's get a calculator. 1 over 1.614. Too bad we cannot key milli. Let's put in the E minus 3. 619. Let's choose a 3 decimal point to be consistent. 619.579. Okay. Just key in immediately here. Key in immediately. 619.579, if I remember correctly. Ohm. Okay, this will be ohm resistance. So the current we determined in the previous step. The current is the current is we calculated here. 7.87 milliampere. Let's come back to the here again. Current is 7.870 milliampere, 3 decimal point. Somehow we need to insert the ohm here, but I'm afraid the ohm won't be able to insert this type of ohm here. You can actually light this text in the center. Okay, now we're left with the last one. You see, this is a theoretical video again. You need to do it manually with your own calculation. Cannot use a software. That's what we use. That's what we mean theoretical. Use the your head to calculate. Instead of using a computer. All right. I think this is it. I want to confirm with you that this is the correct value. 619 is the correct value. The challenge is to find out this value actually. Okay, this is a value, this answer. But somehow we need to put this one in our report, right? We cannot just write down here. So where do we do it? Let's come to the result again. For step 5 or step 6. Step 6. Okay. We need to calculate resistance. R is equal to V over I. Equal to 1 volt over. So take not this number. This number. That's why I need to copy this one into our. Oh, I need a water. That's why I need to copy this into our reports. Step 5. Here, after 4. After 4, make sure they're in the right sequence. Okay, so we take 1 over 1.614 milli, then we can come to the correct answer, 619.58. Let's copy the symbols for ohm. Oh, cannot find here, never mind. Just borrow it from here, insert symbol. Okay. All right. Now we're down to last remaining step. Will be step 7. So what we now dealing with is the RL. We need to find the current through the RL. Okay, let's copy this one. Back to our procedure again. Step number 7. Okay, how come this still here? Strange, huh? Figure 3.3 supposed to be here. Never mind. Let's put the 7 down first. Put the step 7 first. Okay. Now let's move this one back to the way it should belong, where it belongs. Here, figure 3.3, after step 1. So let's read about this statement. Remove the DC source from the terminal AD, press back the RL. Of course, the resistor there is just a dummy resistor. I mean the voltage 1 volt is just a dummy. We need to remove it eventually. Now we need to replace back the previous one, the one we have. We didn't actually throw it. It's the one 180 ohm. So let's get another resistor and place in the gap here. Okay, and change it immediately. 180. All right. 180. Then what? Then now I have selected. Okay. Hey, wait. Am I in the correct step now? Excuse me. Remove DC source between terminal AD. Place back the RL. Now place back the 15-volt power supply. Remove the short circuit and place back the 15-volt power supply. So it's referring to here. So remove the short circuit here and put back the our power supply. Edit component power supply. Place here. 15 volt. Okay, change the 15 volt. 15 volt. Then join the wire. Okay, that's it. That's what they asked for. This is step number 8. So I think we should copy the circuit and then press under the result, because we already modified already. Okay, just make people easy to read our report. We have to show them the modified circuit. Okay, let's get another one. All right, then put into our report under the result. This is step number 8. This is called the simulation. Okay, this is one. All right, everyone ready? Can follow. Let's see. Now we need to record down the current flow to the R. This is easy, right? To measure the current flow through this is easy. That means the current flow through R6. Okay, R6 is RL. So this is very easy, see. The actual current flow through the external loop. This is not the Norton current. This is the current flow to the loop. So now we have the current here. Okay, so if this is the current flow to the RL, we need to make sure the current flow through the R6, not the current flow to the V1, R6. So it must be this one. You need to change it. Okay, you need to change it. So I've already confirmed this is the answer. Of course, we need to prove it in our report. Okay, do the same thing also under the result. Let me see. Simulation result. 4. State that number 9. It's better to show in figure number. See, we forgot to insert the figure number here. It's not a good practice actually. Actually, in your report, you should refer to figure by number, figure 1, figure 2, instead of the refer to the figure above. We should be exactly tell the user to refer to the specific figure by using the figure number. In just instead of using the going here, going there, using the words. Okay, I think you can adjust this one later on, right? Okay, I think it's time for break, another break also. Okay, time for another break. Later we come back, we finish it, we finish it, the conclusion and the last step. I'm back. Let's look at the last step. Where is it? Just now we did the read and record down the current value. Yeah. Okay. Then we this is the last step. Draw the Norton equivalent circuit. Oh, okay. Message. Norton equivalent circuit number 10. Okay, which is our step number 8 and 9. Forgot to do that. Step number 8. Trace back the 15 volt. Remember for every the circuit that we modify, we need to place a screenshot. And then what? The read and record down the value for RL. Okay, read done that. So what I need to do is just reverse it.
Sir, can't see your screen, sir.
Oh yeah, sorry about it. I forgot to share my screen now. So I need to record what I did just now. I was reverse engineering. We already complete step 8 and 9. So I just put back the statement here. And then I insert a new statement for step 10. To draw the Norton's equivalent circuit. So like into a box like this. Okay. So let me show how it looks like. I think you know, right, how it looks like. But let me confirm with you. First, Norton is not dealing with the voltage. It's about the current source. We call the Norton current. And then second thing you remember is the Norton current actually is a parallel. Is a parallel with the current source. The Norton resistance actually is a parallel with the current source. Okay. Let's draw a better line. Okay, this one is to be parallel with the Norton resistance. Okay, it's called Rn. And then extend out is our terminal. AD instead of AB, I think this question refers to A and B. So we need to attach this one to external loop. I will use the dotted line to represent the external loop. External loop. Let's call it Rm. Now let's fill in all the value here. So this one is 7.87 milli. This one is 619 ohm. All right. So depend on whatever external load you want to attach to the output, but the remaining fixed circuit remaining the same. So now the current that we measure using the simulation, current in the RL, current through the RL. Current through RL so-called IRL, right? Is this one 6.108? Okay, 6.108. This is our RL, by the way. 180. 180 is our RL. So what do we do now is just type it in here. IRL is equal to, from the figure, IRL is equal to 6.018 milliampere. Convert this one to subscript. Okay, that's it. If you want to make it look better, of course you can underline it. Take away the extra space. 6.108, okay? Fill in the table. Fill in the table here. Yeah. Another figure. Yeah. 6.108 milliampere. Now we have left these three that need your analysis skill to find out the Norton, their individual values. Okay, individual values. First of all, let's cut and paste this thing here. But this is incomplete one, as you see, this incomplete one. But until this stage, you should be able to get at least three values. The other three value, it takes time for you to calculate it, by yourself, not using any software. So I'm going to put this one under the result also. But three more you need to fill in. Of course, it should be about the same. Otherwise, it doesn't prove that this theorem is working, right? If you're getting a different result, most likely you are making a mistake. So your result here must be tallied with the simulation result. Because I already confirmed with you, this is the correct result. That's why whatever the value you come up with, you have to make sure that it's similar with this one. So let me give you a bit of help here. Okay, let's see how to find a Norton resistor with the formula without using any software. So let's find out the original circuit. So let's look at the original circuit. Let me give some guideline. But we have to take this out. This is not part of the original. Okay, let me show you how to do this. When you're attending the after you're attending the tutorial 3, I think you should be able to do this. Okay, but I'll give you some I shed some lights on this one so that you have some idea. Because there's a trick here actually. There's a trick here. Let me show you how to solve this one. Let me copy the circuit first. So this is a circuit without the output. Okay. So you see, I told you previously, this branch and this branch and this branch, they form the Y connection. See, they form the Y connection. Yeah, it looks like a Y connection. Okay, this one make the things difficult for us to analyze it. Okay, first we want to find the Norton resistance. Norton resistance. That means we need to take this one out, take this one out. So it leaves us with the circuit like this. We have 1.8 still there, 1.8K still there, but the 15 volt has been replaced by the short wire, and then the 3.6? Yeah, 3.6 still there. Okay, and the one on the top, 100, and the vertical one 820, and the last one 100. See, this makes us difficult to find the equivalent resistance. How to find the total resistance here? Because you see, this one looks like it's a series, but this one is parallel also. At the same time, this one is series, this one parallel, this one is series, this one parallel. These two are parallel, these two are parallel, these two are parallel. So it looks really confusing, right? You don't know where to start. Whether start from here or start from here, something like that. Anyway, you cannot find the suitable way to start. So if we can convert this in the center one, if we convert it to from y to delta, probably it will look much better. Let's try it. Let's try it. Let's convert to something like this. Convert to something that easier for us. Convert to something like this. 1. At least these two are sharing the same node, you see? They are sharing the same node now. 2 and 3. And then the top ones still remain, of course, the top one still remain. But the good news is the top one now parallel with this one. You see that not this node and this node are the same. Only two resistors now. So the top one still remain. This one is still there. So we need to find this tree, convert this tree into the delta. Okay, so the formula is like this. Let's call this one the new one. We have to call it a new name. Let's call this one as RC, okay, RC, straight from your notes. From tutorial 1, you can refer to your notes. This is called the RB. This is called the RA. Okay, let's start with RA. RA is given as, you just need to take RA. How do you look at RA? RA is here. RA is here. Okay, RA is here. So RA is between what? RA is between from RA here, you look at opposite side. You look at opposite side here. Here. Oh, I think let me do it the other way. I don't want to confuse anyone here. Let me do it another way. Usually when we are drawing our A, we better to use a dotted line of different color. Dotted line, RA, dotted line. So this RA, you look straight forward into the opposite side. You see this one, right? You see the 3.6K. So you put the 3.6K at the denominator. Then on the numerator, you just put all the combination. R1, R2 plus R2, R3. All the possible combination. R3, R1. Or R1, R3 is the same. R1 and R2, R2 and R3, and R3 and R1. No more else, right? R3 and R2 is same with R2 and R3, right? Same thing. But the denominator is important. Denominator is the one look exactly opposite the RA is a 3.6K. So if you want to fill all in, it become R1. Which one is our R1? Wait. R1 is here, 3.6K multiplied by R2. R2 is here is 100 plus 100 multiplied by R3. R3 is the 820 plus R1. R1 is our 3.6K. Divided by R3. R3 is 820. Okay, then you over 3.6K. Then you will get this RA. Okay, you'll calculate this RA. Then you do the same. You do the same for RB. RB is here. Let me use a dotted line, not to confuse you. So RB will look at opposite is here, 100. So for RB, it's going to be the denominator is 100, and the top is the same. So you just need to calculate once only. The numerator is the same, but the denominator is 100 because RB is here. You look opposite, you get this one. This is the angle, right? Then opposite is this one. Because the way I draw it is look it very difficult for you to refer to, right? So if you really draw a real Y, if you put your RB here, then you make it start to make sense already. You put your RB here, okay? So this one looks like opposite, right? These two are adjacent. These two are adjacent to RB, but this one is the opposite to RB. So this one is actually the 100 here. These two is the 820 and 360. They are adjacent to the RB, but the opposite one is 100. So the opposite one you put at the denominator. So I'll see the numerator will be the last one to 820. Okay, after you convert it, then it becomes something like this. Okay, so you just need to find what is the total resistance here. What is the total resistance? Looking into terminal A and B. These two are parallel. Okay, then what? Then this one will reduce to 1 only. RC and 100 will combine into 1. These two combine into 1. And this one stand alone like this. So what you hear is that everything in series. This is not parallel, right? Because this knot is sharing with this guy, but another knot is sharing with another guy. So they are all parallel. So you end up with let's call it R X, R Y, R Z. Okay, then our EQ will be sum of these three, Rx plus Ry plus Rz. Then you can find a Norton resistance just like that, you know. This is what I remember, see? This is what I remember. I'm sure this is still applicable. Okay, so you can go ahead and try it. Go ahead and try it. Whether see you can come up with something that matching the simulation result. That is 619 ohm. Okay, because we don't have enough time to run through all the simulation, all the value. But it's still another homework for you to do. You see, it's treated as an assignment for you to practice how to come up with this value by using your own calculation. 619, as long as it's something close to 619 will be fine. You see, doesn't need to be matching exactly the same. Okay, so by doing this, I think you can come to 619. Okay, if you skip this part, if you didn't show me the how you get the theoretical value, then I have to deduct some marks actually. I have to deduct some marks. Hey, hold on, guys. Let me check something here. Check something here. Yeah, you need to show me. Okay, you need to show me the step by step. Actually, I think it mentions step by step, if I'm not mistaken. We actually mentioned that you need to show the step by step. Where is it? Read and record. Where is it? Cannot find it. To determine the theoretical value, or it didn't show here. Or here, compare the simulation result with theoretical value. But I didn't ask you to calculate the theoretical value. But somehow you need to do this also without using the software to compare it with the theoretical value. Okay, let me quickly see that whether any of the previous student, whether they can do this or not. Let me see. Let me see any one of them can actually come up with the theoretical value themselves. And let me have a look. So we hold on for a while. Let me see whether the previous student here he can come up with a calculation or not. Therefore, I can share with you also. Hold on, yeah, now reaching the page already. Oh no, this student cannot do it. This student skipped the theoretical value. He didn't show the theoretical value. Let me make sure that. Oh, it's a different circuit actually. There's a difference. Let me see that. Is it the hold on, hold on. 820. 820 must be taken out actually. 820 must be taken out. I don't think it's correct. I don't think it's correct. Something very I don't think this answer is correct. Okay, you try to do it yourself. You try to treat it as a challenge question. Try to find that whether you can solve this already or not here. All right, let's proceed to the next question. Okay, let's proceed. This is the question actually. This is a question. We still need to copy this one. Oh, I have from here. Where is it? Yeah. So after the result will be a discussion. And then by the conclusion. Okay, then you need to put your question here. You need to put your question here. Are they close? If not, give a reason. Okay, these two must be bold and 14. Okay. Yeah. Yeah. Okay, that's it for question 3. Remember, you still have time until the November. So wait until you have sufficient knowledge to solve this issue, to solve this problem. Then you come back, visit here again to solve for this theoretical value. Because we are not supposed you to, we are not expect you to complete everything today, you know. That's why the date is not this week or next week. It's the 2 months later. So it means that you still need to go through some tutorial in order to find the to fill all the missing information. All right, let's save this one and insert another page break. Now we come to question, the last two questions already. Now we come to the last two questions. Superposition, another theorem. Okay, look at this another theorem here. Superposition. Let's quickly go through this header. Hey, wait a minute. I need to stop my recorder here and start the new one. Because this is another question already. Just already stopped there, right? Okay. I need to stop the recorder for a while.